Lesson 8, Graphs of the other trigonometric functions. In this section, we're going to look at two of the reciprocal functions that have been established in previous lessons, cosecant and secant. In order to come up with what the graphs for both cosecant and secant look like, we need to be familiar with the graphs of sine and cosine. Cosecant, which is the reciprocal of sine, means that we should be considering what the graph of sine looks like, which is what I have repeated to the left of my image. The graph of sine typically begins at the origin of 0, 0, increases up to 1, and then decreases back down eventually to -1 until it reaches back up to the x-axis. If we use this, we should be able to come up with where the graph of cosecant comes from. The graph of cosecant is taking each of the values established for sine and taking the reciprocal of each of those. So, for example, in a t-table of x and sine of x values, this graph of sine would have 0, pi halves, pi, 3 pi halves, and 2 pi. And sine values there would be 0, 1, 0, -1, and 0. Cosecant, though, at each of those points would simply be the reciprocal of the sine value at each of those points. So, for example, the reciprocal of 1 is 1. The reciprocal of -1 is still -1. However, each of the other points there that are all equal to 0, sine of 0, sine of pi, and sine of 2 pi, the reciprocal of that does not exist. So, we really know only a couple points if we use these 5. Those instances where sine would equal 0 and cosecant does not exist means that we are going to have a vertical asymptote in place of each of those, which is what you see in our graph for cosecant here. We have an asymptote at 0, an asymptote at pi, and an asymptote at 2 pi. For the other established values, we have pi halves is still +1, and 3 pi halves is still -1. Where these other curves come from, however, come from the trend of what is happening to sine as we go from either the peak or the trough of sine towards the x-axis. If you think about what is happening to the y-coordinates here, from the peak of the curve for sine, as we go towards the y-axis, the y values are getting progressively smaller. Cosecant, which would be the reciprocal of that, would therefore be taking the reciprocal of a number that is getting smaller and smaller and smaller. And what happens when you take the reciprocal of a decreasing value or a very small number is that you instead get a very large number. So the values of sine that are getting smaller cause cosecant to get progressively larger. This should also make sense if you consider cosecant as the ratio of hypotenuse over opposite, as at its most extreme, we can have a consideration where hypotenuse and opposite are equal, if you just have a straight line. However, in any typical triangle, the hypotenuse should be more than the opposite. So, in these cases, we should expect an increasing amount from this bottom point at 1. That way, for example, when I get a point of 2 up here, that would imply that the hypotenuse is 2 times the size of the opposite, which would make sense in right triangles. With this now, we should be able to establish the domain, the range, and the symmetry for cosecant of x. The domain of cosecant of x is not going to be the same as the domain for sine. The domain for sine was all real numbers or -infinity to infinity. However, in this case, cosecant has many asymptotes. The asymptotes, though, do seem to be relatively periodic. And by that I mean that they show up at typical intervals. They show up at 0, at pi, at 2 pi, and you can probably expect that the next asymptote would be at 3 pi. Therefore, the domain would be all numbers except where we have those asymptotes. One way of denoting that in set notation would be to say that x such that x does not equal pi times k, where k is an integer. That would be the set notation way of denoting this. For the range are all possible y values. And again, the range is not going to be the same as sine. The range for sine was -1 to 1, which made sense for ratios of opposite over hypotenuse. However, in this case, the range here actually spans down to really any number up to -1. And then there are no values of y in between up to where I get to +1 and up to increasingly large positive values. This means our range can be denoted as -infinity up to -1, which is inclusive, as well as 1 up to positive infinity. To link these two sets together, we will use a union. The symmetry of this function, however, the symmetry of cosecant does share the same symmetry as sine, which means it is also an odd function. This means that if we have a negative input inside of cosecant, we can take that out in front of the function. In terms of all the other information, yet again, we can say it's continuous and smooth over its domain because the domain does not include those asymptotes. Again, this is more of an important concept as you go further into mathematics. However, I'm going to add to that a couple things. First, I'm going to say that the period of the function is 2 pi, which again, it shares with sine. It still takes that long for it to repeat itself. You look at this part of the curve where it seems to have increasing on either side. That does not happen again until over here, which would be at 5 pi halves. Meaning that this still has a period of 2 pi, or that's how long it takes for it to repeat itself. I will also say that it has asymptotes at pi k, where k is an integer. That is why those values are taken out of its domain. You will see a lot of the similarities in the discussion here concerning secant as you did in the discussion for cosecant. If you notice for a secant, we can come up with this graph based on what we know for cosine. For cosine, which I have the graph listed here on the left, the x and cosine of x coordinates that are used to create this, using the 5 quadrantal angles of 0, pi halves, pi, 3 pi halves, and 2 pi. Cosine at each of those values are 1, 0, -1, 0, and 1. However, secant of x, which would be the reciprocal of cosine, would flip each of these values over 1. So 1 would still become 1, -1 is still -1, and 1 is also still 1. The values of 0, however, would now become 1 over 0, which are not defined or do not exist. Meaning we have asymptotes at pi halves, 3 pi halves, and we would continue to have more asymptotes in this periodic function. That means the period for secant can be defined then as x, such that x does not equal any of the asymptote values, which are not the same as the cosecant ones, which were at pi k. The secant asymptotes are at pi halves plus pi k. Again, where k is an integer. The range, though, for secant is going to be the same as it was for cosecant. This also has a range of -infinity to -1, -1 being inconclusive, union with 1 inclusive up to positive infinity. It includes all negative ratios up to -1 and all positive ratios from +1 and up. The symmetry for secant is going to be the same as the symmetry for cosine, which is that it is even. That means if you have a negative input on secant, you can take that out in front of the function. In terms of other information, again, it is continuous and smooth over its domain, which does not include the asymptotes, because the asymptotes are not part of its domain. Aside from that, we have that the period of the function is 2 pi. Yet again, it takes that long for it to repeat itself. You can even see that in the graph for secant shown here. If you count from the point here on the y-axis where we have a part of the curve that trends upward, that does not happen again until we get to 2 pi. And I'm also going to point out that the asymptotes are at pi halves plus pi k. Those are the functions of cosecant and secant graphed on the Cartesian plane and their properties.